So this is the first section in chapter 5. If you haven't printed the notes yet, you can do it later, or you can pause now and print them now. But anyway, I will probably be going too fast for you to copy at the same time. I will be gliding over information that is straightforward, and I will be focusing more on elements that I think are worth commenting on. And these green ticks on the side, nothing for you to particularly wonder about. It's just notes for myself where there are things I believe I need to talk about a little bit more. Section 5.1, though, is going to draw on a lot of things that we have an original understanding and knowledge of, so it may not be the most complex section. So the objectives are to look at some basic concepts of geometry in Rn, like lengths, angles, and orthogonality. We will look at the concept of projecting onto a subspace, and we will use an orthonormal basis. This is not the same as orthogonal for projections. So a few definitions to start with that you will recognize. Firstly, perpendicular and orthogonal. The meaning of that is if two vectors are perpendicular or orthogonal, then their dot product is 0 and vice versa. The second is length. So we know what the magnitude of a vector v. What's interesting here is to look at this formula and what it means. In the process of learning math at school, you've certainly learned about lengths earlier than you've heard about dot product. Dot product comes much later, but in fact what we see with this formula is that the dot product is more of a primary concept in mathematics, if I can say. It's deeper into the foundations of mathematics than magnitude. And why is that? Well, because if you have defined a dot product, if you know what the dot product is for vectors, then you can define what the magnitude is, because the magnitude is the square root of the dot product of a vector with itself. Think about how this is true for simple examples. If we have a vector 3, 4, then we know that the magnitude of that vector is 5 using the Pythagorean theorem. Well, the dot product of the vector 3, 4 with itself is going to be 3 times 3 plus 4 times 4, which is really what we're doing when we're doing Pythagoras. So it corresponds to this, and the dot product allows us to define a length or magnitude. Unit vector, we know orthogonal. Two vectors are orthogonal, it was explained above, but what is it to be orthogonal to a subspace? It means that a vector is orthogonal to each vector in the subspace. So think of a plane in space. So, and now if you think of a vector that's perpendicular to that plane, it is perpendicular to each vector in the plane. Finally, orthonormal. This is a dangerous word because it looks like orthogonal, but it's not the same. Orthonormal means orthogonal plus unit vector. It's the ideal situation when we were working in multivariable. Our basis was ijk, vectors ijk. They formed an orthonormal basis because they were all perpendicular to each other and they were all unit vectors. A simple example follows showing that these two vectors form an orthonormal basis. You can check by verifying that yes, they are perpendicular because the dot product is equal to 0, and yes, they are both unit vectors because their magnitude is 1, so they form an orthonormal basis of R2. Here's a similar example. We have 3 vectors, but this time we are working in the 4-dimensional space, and we are wondering if they are orthonormal. So we need to check the same things as before, that they are perpendicular to each other, which is done here, and we cut a little short in class because it's the same calculations every time, but you can see indeed that U1 is perpendicular to U2, U1 is perpendicular to U3, and U2 is perpendicular to U3. And finally, we need to check that each of them is a unit vector. We can just do it once for all of them. 0.5 squared plus 0.5 squared plus 0.5 squared plus 0.5 squared. It all gives 0.25. So if you add them up and take the square root, you find that it's equal to 1. Now the second question is, if we want an orthonormal basis in R4, we are missing one vector, we only have 3, and of course we need 4 vectors to form a basis of R4. So what would U4 be equal to? This is kind of a checking game. You have to figure out. Obviously, it's going to have the same kind of appearance as these vectors, but you just have to find where to put the negative signs in front in order for U4 to be perpendicular to the other 3, and this is one of the 2 possibilities. So orthonormal vectors are linearly independent. That's a theorem. Absolutely, obviously, since they are perpendicular, they are linearly independent. And if we have n of them, it's important to see that there's an n here, then it forms a basis of Rn. Now, when we have a vector x in Rn and we have a subspace V, we can always write the vector x as the sum of 2 vectors. We can always say that x is equal to, I say x perpendicular plus x parallel, but we will see in a minute that this x parallel is the orthogonal projection. I just say x perpendicular and x parallel because it makes it easier. So what are these 2 vectors? One of them, x parallel, belongs to the subspace V, and one of them is perpendicular to the subspace V. So let's look at the sketch here. It's in 2D, but it shows the situation quite well. So it's R2, it's the plane, and our subspace V is this line. So if we take any vector x in R2 here, we can always express it as partly a vector that is in the subspace V plus a vector that is perpendicular to the subspace V. It makes quite a bit of sense, and that is always true wherever we are in R2 or in R25. Now the second thing that is said in the proposition is that if you split a vector x into 2 parts like that, following these rules, there's only one way to do it. Again, if you look at the example here, it's quite clear that you're not going to be able to find another blue vector and another perpendicular vector that add up to x. There's only one way to do this. So definition, this x parallel that I called is actually called the orthogonal projection of x onto V. So if we look backwards now, not at building x from blue plus black here, but projecting x perpendicular onto the subspace, we get the blue vector. This act of projecting perpendicularly is a linear transformation. What does that mean? We've said it so many times, but it's so important to remember. A linear transformation is a transformation such that t of u plus v equals t of u plus t of v, and also t of k times u equals k times t of u. So if you add 2 vectors and you project them, it is the same as projecting the first vector and adding it to the projection of the second vector. Alright, one theorem now. If V is a subspace of Rn, V has m dimensions, and the basis of V is u1, u2, etc. to um. So m is smaller than n, or smaller or equal to n. Then if we want to find the projection of a vector x, we only need to do the dot product of each of the bases in vector subspace V with vector x. which is why it's so useful to have an orthonormal basis. Sometimes it's quite hard to find what linear combination make a projection, but if you have an orthonormal basis, it's very easy. We'll see in an example below how it works. So a note here, if you project a vector, and in this example we are in space and the subspace is the xy plane, so the floor here. If you project a vector from R3 into the xy plane, here's the result. This vector here is the result. What you can do is project on each of the vectors in the subspace. So the projection of x on the first vector of my subspace would project down here. If I say that my first vector in the subspace is vector I, so it spans the x-axis, then if I project vector x onto the second vector in my subspace, so on vector j, it'll project down here, and then I can add these two vectors and I will get a projection onto the entire subspace. So this is what is shown here, that the projection of vector x is going to be the dot product of x with each of the vectors in the basis times the vector in the basis. So here's an example that is a bit richer. We have a subspace V that is spanned by vectors u1 and u2, and we wonder what is the projection of 4, 2, -1, 7 onto that subspace. So if we want to apply what was just written above, we need to make sure that u1 and u2 form an orthonormal basis. And that's a constant mistake of students. Every year, multiple students make that mistake of not checking that we do have an orthonormal basis and just applying the formula that is here without checking. So we need to check that these two vectors, u1 and u2, are perpendicular and that they are both unit vectors. If they aren't, we cannot use the formula. So we know that they are because it was in one of the exercises on the previous page. The magnitude is 1, the magnitude is 1, and also if we take the dot product, we will get 0. So the projection of x onto the subspace is going to be given by this formula here. And Say didn't quite finish question A. Here we need to calculate what is the dot product of x with u1, and it's done here, so the result is 6. So it should what's missing here is to write equal 6u1, and then the dot product x2 with u2 is -3, so it should be equal to 6u1 minus 3u2. That's the answer to A. And then what is the projection in the original base? In the original basis, we just expand, we just calculate, so this is the continuation, and we get this solution here. So very remarkably easy to find a projection, which, as you remember from previous sections and also from multivariable, is quite a complex concept, and it might be really difficult and fiddly, but if you have an orthonormal basis, it's absolutely straightforward. So here's the same formula again. The difference here is that this is not a projection, it's just if we have Rn, so the full space Rn, we can always break down any vector like this. So what it means is the coefficients of the vectors are given by the dot product of it with each of the vectors in the basis. So I'm explaining this again in the note. Okay, so we see already that we're going to be skipping something. Good news. The definition, the orthogonal complement of V is written V perpendicular like that, and it is made of all the vectors that are perpendicular to subspace V. And what's interesting to know is that V perpendicular is actually the kernel of the projection. So here's an example, an illustration. If V is a line, then V perpendicular is the plane perpendicular to that line. And vice versa, if we said that the red part is V, then V perpendicular would be the blue line. So it kind of reciprocates back and forth. So these are information that show up in this theorem here. Firstly, V perpendicular is a subspace of Rn. And there's a little proof here. Since V perpendicular is the kernel of the orthogonal projection, we know that the kernel is a subspace. Second property of V perpendicular, the intersection of V and V perpendicular is the zero vector alone. There is no vector that belongs to both V and V perpendicular. How would you go around to proving that? Well, think of the dot product. If a vector x is in both V and V perpendicular, it means its dot product has to be 0. And what does that mean? It means it's the vector 0 only. Another property comes directly from the rank nullity theorem. And finally, last property that we list here, V perpendicular is equal to V. So we flip back and forth and we fall back onto V. So, okay, we are not doing the proofs this year either. Pythagorean theorem. This is important because we know the Pythagorean theorem, but now we can look at it in the light of linear algebra and in the light of defining magnitudes of vectors. So the magnitude of a vector, as we saw originally on page 1, is the square root of the dot product. So for the Pythagorean theorem, we're actually taking the square of the magnitude, so we won't have square roots. But what is the magnitude of x plus y? It's defined with the dot product as x plus y dot x plus y. And if we distribute, this is something quite remarkable that we tend to not realize. The dot product is a product, and so we can distribute. We can distribute, say it's x dot x plus 2 times x dot y plus y dot y. So we reach this line here. Now, what does the Pythagorean theorem actually say? It says that the magnitude squared of x plus y is equal to the magnitude of x squared plus the magnitude of y squared, provided we have a right triangle, provided x and y are orthogonal. So x would be like this, and then y would be like that, and x plus y would be like this. So provided we have a right angle here, the Pythagorean theorem applies. So we reached this row. Now, when is it going to be that this row is equal to that? Well, if 2 times x dot y equals 0. What does it mean if x dot y equals 0? It means exactly that x is perpendicular to y. So a nice little proof of the Pythagorean theorem using the dot product. Two more things. First proposition here, the projection is always less than or equal to the magnitude of the vector it is projected from. If you think of yourself and if you think of your shadow as the projection of you on the floor, you may think that sometimes your shadow is longer than you. When the sun is down, it may project a shadow that goes 2 or 3 or 4 meters away from you. But we are talking in this section of orthogonal projection. So we are always projecting perpendicular to the subspace we are projecting on. So if you want to think of your shadow, you have to think that the sun is perpendicular to the ground, so it's vertically above the ground. And in that case, you'll realize that your shadow is never going to be longer than you. If you want to be as long as possible, you're going to have to lie on the floor, and then your shadow's length will be equal to your length. So how does this work? We start by splitting x into the two components that we saw before, and since we know these two components are perpendicular, we can apply here this equal comes from applying Pythagoras, and therefore we can see that this must be greater or equal to the magnitude of the projection squared. If I look back here, there's a little square missing here. No big deal. Okay, Cauchy-Schwarz inequality states this, and we're cheating a little bit. We're going back to multivariable, and we're seeing that the dot product of x with y is equal to the magnitude of x times the magnitude of y times cosine theta. And if you think about it a little bit, you'll realize since cosine theta is always a number between -1 and 1, you can identify this with what's highlighted here, and you will see that naturally it has to be true. Lastly, the theorem, Cauchy-Schwarz inequality, is equal only if x and y are parallel. If x and y are parallel, cosine theta equals 1, so you will get x dot y equals magnitude of x times magnitude of y. X and y can also be parallel going in opposite directions. In that case, cosine theta equals -1, and that still works because there was an absolute value here. So that's it for section 5.1. Thank you very much.